join. My name is William Atencia. I'm a big data engineer here in Subserve. I've been in the company for almost 2 years in two different periods. Fun fact. So today we're going to talk about vector database. Um, I will show you the agenda in a second. Yes, there. So we're going to talk about what are vector database, the architecture, the components and how they work, what vector databases are used for, the tools we have available in the market for vector database and their particularities, what are those tools better suited for and their specific use cases, what are the best practices. I have a vector database demo using NLP, and at the end of the presentation, I will give you my conclusions or what I think is important to keep in mind when working with vector databases. Uh, yeah. So what is a vector database? A vector database is an specialized database designed to store, manage, and index high dimensional data. Which type of high dimensional data? So it's better suited for for sounds or for images and text. And those are the kind of sources I think are more relevant because when we work with those kind of data, we don't have like a proper way or tool to directly connect or to directly associate different files. For example, if we have two different tests but talking about the same topic, for example, a newspaper talking about current state of football in Europe, just to say something. Maybe the words are different, the phrasing is different, but at the end, the semantic relations between both news should be similar. We're all talking about current state of football in Europe. So those are the kind of things we try or we will accomplish when working with vector database and this type of data. So, and these are important because these allow us to scale to a point or to scale to a size that we couldn't in the past because we obviously have SQL and NoSQL, and we can store or extend their capabilities to try to work with vectors, which will be a representation of the source data that I mentioned previously. But when the times arrive to scale to multiple millions, even billions of different vectors or embeddings. I will be using in both terms are across the presentation, but both mean the same. When I say vector or embedding, is a numerical representation of the source data we receive. So getting back to the point. So this is important because we now don't have the necessity to connect two different vectors using straight data to connect them. So if they have a difference between them, we still will be able to associate them because of their semantic sense in them will be similar. Again, like the example I gave you from a newspaper, but could be also a video if I have data of or videos in the beach or images in the beach, they will share similarities in the embedding. I will talk in a moment about how this embedding happens and things that we need to keep in mind when doing it. So now talking about like the overall components that we have in this type of system. First, the data, high dimensional data, as I told you, data that don't fit in traditional table databases. We have an embedded model that will convert this data from their native source into a numerical vector. Well, obviously the embedding or the vector, and finally the vector database where we will have the results, the embeddings, allocated, and we will be able to retrieve them and to use them for different purpose that I will just mention. Any questions up to this point?
Uh, I have an obvious question. Can we expect that any type of data like audio, video, and text data about the same topic will be in the in the close neighborhood. Uh, so vectors for all these documents of different types will come to the close neighborhoods in vector space.
Okay, we can achieve that, but it's not a straight process. Even in the um, in the demo that I will present you, I will show you just a case when that doesn't happen, and I will explain why. So again, we can achieve that. So if we have a video of European football and news about the European football in, I don't know, some kind of podcast related to the same topic, we will need to extract the data first and align them probably in test, so a transcription of those, or have some kind of metadata that connects the data to those topics. And we can do that. Most of vector databases allow to include metadata fields or multiple metadata fields to like to separate them about the topic they or the purpose of each data as I mentioned. So we can add a metadata field called topic, and we can put in that topic European football, and it will be the same for the video, for the new, or for the podcast. And at the end, they should be closed in the vector database, obviously depending on other.
I I
Yes.
see. I see. Well, yeah. What I expected was some magic which can bring all the topics, all the data about the same topic in the same place with some magical
Yeah,
means, not not
it,
not with preparations. Yeah.
Yeah, I mean, it's there are special cases, I mean, special models that convert the source data and do a multimodal embedding. So probably that will work. I haven't tested, but I think it's somehow possible. But again, I think that it will need an extra layer of metadata in order to be properly separated or clustered, uh, having different sources, because obviously the type of data you're extracting from a video and from a test will look different in the embedding model. So everything
Yeah.
depends on the embedding model. I will get to that in a second.
Yeah. Thank you, and sorry for distracting you.
No, no worries. That I think this interaction is good for the presentation. I don't know how to. Yeah. So now getting to the architecture of vector databases, we're going to get a little bit more deep into each of their components. So the key component here that I have mentioned and I have not explained is the embedding model. Oops, I don't know how to get back. Oh, here. Yeah. So what the embedding model does is convert the data that we have available into a representation of numbers in a vector or array. And yeah, so what we achieve with this is similar uh, data should have a vector resulting similar between them. So if I convert an image of two dogs that are somehow yeah, a dog, for example, they should have similar resulting vectors, as both should have very similar characteristics in the image, in the two different images. So we have multiple types of embedding model. We have many options in the market that we can test and that better suits our necessities. We have to take into account different factors, what we are trying to achieve. For example, we have embedding models specifically for English. We have for Chinese and other languages, but we also have a specific embedding model for image, for video. I will tell you some examples later. So yeah, we need to take into account what we're trying to achieve, the scale we need, and those type of metrics that will help us to properly pick the embedded model that it's a better fit for our purposes. So the next thing that we need to understand is nearest neighborhood algorithm. So as I just mentioned in the previous slide, vector databases work based on distances. So we need to pick which is the best algorithm based on our resources and our purposes and our size. Uh, in order for the application, the final application, when we query and we have a result or similarity results to work better, it's because I will need to pick a different algorithm if I have less, let's say a number like less of 1 million of vectors. Uh, the solution we will need will be different if we have billions, because other factors came into the equation, such as velocity, memory, and obviously our purpose. Do I need uh, the best or the most accurate result, or do I need velocity and just a few similar examples? So those are the type of things that we need to take into account when designing our architecture for our application. So next thing is distance metrics. So we have different distance metrics. Again, we have vectors, and we need to determine which one are closer to others. So we need to pick the right metrics. We have multiple metrics, such as cosine similarity, Jakarta distance, and for example, uh, if I'm working, if it's very important for me that the how to say it, like to have the most accurate uh, possible solution, then I will pick a distance metric. Probably I will use cosine similarity, or I will use a, a internal product multiplication. So yeah, we need to pick which one is the best distance metrics for our case. We have most of the vector databases that I will mention in a moment have many options available, and we need to test and read about which one is the best for whatever we are trying to achieve. And finally, we have the vector or the embedding. And yeah, there are other things we need to take into account when generating the vector. For example, if I need an sparse vector, Um, an sparse vector is just a vector, but has the majority of the values inside of it are zeros, and only a couple of them are not. And this type of vectors are useful when we need a very accurate comparison. For example, if I'm trying to match words, keywords, an sparse vector is useful because we will have zeros in the majority of the vector, but we will have a value in those important words that we are trying to match, just to say something. Yep. Okay. So I will get a little bit deeper into the nearest neighborhood algorithms. So the the easiest one, or the easiest to understand, is flat. In the flat algorithm, we don't process the vector. So after we use our embedding model and we have our resulting vector, that's what we are gonna use to calculate distance. So we have this high dimensional vector, probably with more than 300 values in it, and we are gonna use one of those metrics that I just mentioned, probably cost cosine similarity, to determine which one is closer to the one that I'm querying. So if you see, in this case, we have queen, and it's close to woman, then close to man, and then close to king. So all of these are based on the numerical calculation, straightforward. So the second one is local sensitive hashing. And in this case, what we do is we pass our embedding through a hashing layer, obviously with a hashing function, and we'll allocate um, our vectors or similar vectors into buckets. So probably woman and queen will be in one bucket, man and king will be in other, and so on. Uh, Obviously, we have disadvantages in each one. For example, flat, the calculation or the retrieval is uh, very accurate because we are calculating distance straight from the vector, but it's slow at the same time because if I have to calculate the distance between vectors with more than 300, 500 values, it will be a slow process if I have billions of vectors. So flat is more suited for small applications when we have maybe thousands, not millions of vectors. Local sensitive hashing is more useful when we have uh, not high dimensional vectors. So uh, the number I saw, I remember where I was reading was 128. It's already big uh, a big vector for local sensitive hashing. Um, Hierarchical navigable smallware. Basically, we build a graph and we calculate or condense the distance between nearest neighborhoods using the edge of the graph. Yeah. Uh, well, again, we when we're building this type of applications, we need to do a trade-off between accuracy, velocity, and also memory. So hierarchical navigable smallware doesn't consume a lot of space in memory, but build the graph is slow. So the indexing part of the process will be slower compared to LSH, for example. Okay, and finally, inverted file index. So here what we do is build a Voronoi. Uh, I forgot the name. Oh, it's not there. Yeah, a Voronoi diagram. So we create clusters based on the vectors we have, and we determine a number of cells or nearest cells that we will search on. So I will get to the next slide so it's easier to see. For example, here we are querying this red dot and it's allocated in this specific cell. And the number of cells that I determine in this specific image to look for is 1. So it will only look uh, the nearest neighborhoods that are inside this cell. But if I select a highest number of cells to check, maybe I will have, I don't know, maybe if I select 5, so I will have these 1, 2, 3, 4, 5 cells, and probably not this one on this won't be the only result, but this one right here and the one right here. And as I mentioned, we need to be careful when we pick a method because, for example, this one has some disadvantages when we have many data points near to the edge, because in these cases, probably we could have a very close neighborhood in other cell that is not inside this one. And as I have an M proof of 1, I won't check that nearest cell. So it's a trade-off always. We need to review the specific data to properly pick or select the method we want or we need to use. Okay, so there are multiple vector embedding tools. I mentioned a couple of them here. These are like the most popular. And I want to give an special mention to Hugging Face Transformers. We have something called massive test embedding benchmark. And here, basically, we have a list with the ranked models that we have for embedding, and they are split by size, by functionality, by language. So, for example, if I'm trying to summarize, or the the goal of my application is to receive a test and summarize it, we have specific models for that. If what I want to do is to have the closest distance between, or semantic distance between tests or whole documents, maybe I should pick another model that better fits that purpose. So what I'm trying to say is we have many options that are there available, ready to use, and with a very slow learning curve. So if you are interested in this topic, you can go to MTV and you can pick a model and try if it works for you. So for the one that I did, I was obviously the resources are constrained, and my 8 GB laptop, it's a big constraint, so I have to pick a very small one. But you will see have very good results even compared to other models. So the one I use only, or the one I pick only use like 1.6 GB of memory, and you can see others that use 30, 50. So again, it's depending on the case, the resources, and what you're trying to achieve. The others, for example, OpenAI ADA, this is for text and semantic relations. Clip if for video, Mini LM is similar to OpenAI, but use less resources. So yeah, I encourage you to get a little bit deeper. You will find fun stuff to work in the weekends. Okay, so now I will talk about the most popular vector databases. So we have multiple resources available up there. I picked like the most popular ones, as this is somehow a hot topic, and all of these are growing and each one have a big community. So yeah, Mailbus, which is the one I picked for the demo, is open source. It's available as a managed cloud service. It's called Sealy, I think, with a Z, and also as a Python library. So I picked the Python library. I don't want to pay. Python is managed cloud based, so that's a constraint as you'll need to pay it. And for example, the the nearest neighborhood algorithm they use is proprietary, so you won't have access to modify any of the internal parameters they use for it. That's a little bit a constraint, but also has many out-of-the-pocket functionalities that could be useful for your project. Elasticsearch is intriguing, I would say, because let you work with both works. Uh, I mean, matching full test. So if you find or you are looking for a very specific sentence, uh, you can match it, but also have vector databases capabilities. So when the first one fails, you can set, or you can even select the weights that each search will have, the full test and the vector one, and you'll have somehow an hybrid result at the end of your query. So that's interesting, depending obviously in the use case that you are planning to give. And Weavite is similar to Pinecone, but here we do have a standalone mode, so you can run it in your laptop. And both are similar. Weavite is, uh, I will say, it's growing because they have a lot of functions ready to connect with LLMs and other type of AI applications. So that's like the niche they are trying to explode to grow in the market. So I invite you again to read about those and see if if they sound interesting to you. Maybe you can pick one and do a small demo and continue growing the community. Oops. Yeah. So summarizing things that I've been uh, saying along this presentation, the best practices for vector database. So first, the parameter selection, again, in the distant metrics we use, and the indexing technique we use, obviously depending in the data we are working, the purpose of this data, what I'm trying to achieve, what are my resources. So all those kind of parameters that we need to take into account when building our application. Obviously, the data quality, if we don't have a proper processed data, we could build the best application ever, but probably we won't have the expected results as the thing we are feeding our architecture with, it's not set, or yeah, it's not set for our goal. And finally, cost management. Again, it's always a trade-off between constraints. So we need to take into account uh, what are my resources, my computing resources, money resources, my time available, uh, what is my goal. So we need to combine all of these things all along the process and continuously evolving our development so we can end up uh, with the best solution available for our purpose. Uh, any questions up to this point before I go to the demo? I will take that as a no. Yep. So let me share my other screen. Please let me know when you can see it.
Yes.
Okay. Yes. So here, this part is what I mentioned about MTV, Massive Text Embedding Benchmark. As I mentioned, we have a rank with models based on all these characteristics. And as you see, we have different purposes. For example, the one that the question at the beginning, multi-level classification. We have also English, Chinese, French, Polish, Russian. So depending on what we're trying to achieve, we'll have a specific model that could work for us. We also need to take into account memory usage. As I mentioned, look at this, it's almost 30 gigabytes in memory, but you can find models as small as this one, less than a gigabyte. So those are the kind of things we need to take into account. And aside licensing, but that's more a very specific topic. Yeah, for this demo, I pick this specific embedding model. As I mentioned, very uh, drive by memory concern. So this one is small and easy to use, and you will see the results in a moment. So, okay, so here we have it. This one is using not still not this model. but the one that is native from Milbus, I don't remember the name. It's a very cryptic name. I will pin it in the chat later. So I will look for which car brand is the best. And the dataset I use is one dataset that Quora released. And basically the structure is question one, question two, and the final field is if the question is duplicated. So yeah, so I use that. So as you see, this is somehow a question that we could find in Quora. So I will give it search. Just a second, it's running. Yep. So, well, you can see we have three types of results. We have dense, we have sparse, and we have hybrid. So dense, we use, I use flat for dense. So this use the whole vector to find the closest neighborhoods. So which car brand is the best? You see the results are very similar. Obviously, it's not 100% perfect. As you can see here, this is talking about a PC, not a car. And this one is about roller skates. But as you see, somehow they are close. A roller skate, a car, it's the same principle. The second one, it's sparse. Here, the goal is to match to a more, how to say it, a more detailed comparison. You see, it's completely off. And I will say a comment about that in a second. And finally, we had hybrid. It's a combination between the two. So I gave a weight to each one, and based on those weights, picks the one with like the more appropriate based on the weights. So remember the question at the beginning, trying like to have all the vectors from different sources is close, even if it's a video, a podcast, or a new. I mean, it's something somehow achievable, but there's a lot of things we need to take into account. So as you see, these two are completely off, and that's because here I use one embedding model and the one that uses parts is a different model. So probably works differently. The way they generate the embedding or the vector works different. They extract the semantics different. So even though they are using the same dataset, you see that the difference are the results are completely different. And you will see how this compares against when I use the same one for all. So just a second. Yeah. So here I pick, oh, sorry. Here I was picking this one. I said the contrary, I was wrong. So here I use this model, Stella EN 4 million version 5. And here I use the native one from Milbus in all three results, dense, sparse, and hybrid. And you will see how the same question has at least similar results between dense and sparse. Yes. As you see, for example, we have in dense, we have which car has good build quality in India, and in sparse, we have what are best car gadgets and tools. You see, these are very similar. And again, in the hybrid response, you do a hybrid between trying to match exact words and dense, which is more related to semantics. And we end up with a more suited final answer. So this is similar to what we can found in Elasticsearch using the hybrid option. So again, as I mentioned, even if we have the same dataset, the embedding model we use is very important for the result we have. So again, we may have a condensing model that could understand the semantics between different sources, but it's harder. So that's when we can use a more straightforward tool as metadata. So we can achieve the results we are trying to achieve. Any doubts about the demo? Something you would like to know? Nope. Well, I will get back to the presentation. I don't know how. Okay. So finally, conclusions. Well, before jumping into the conclusions, this is the things we're trying to achieve with vector databases. You see, on one side we have animals, the other side we have fruits, and the representations or or the vector representation of both are completely different, but between categories it should be similar. So each time we query one of those, we'll have a fair, quick response and related obviously to the topic we are looking for. Okay, and the conclusions. So vector databases, as you saw, it's a powerful tool when we are handling high dimensional unstructured data because we can extract semantics or meaning of the source data without an extra processing. We're just using our embedding model, and after that, we pick a metric, an algorithm to select them, and in distinct, I mean, no matter the combination, we should have a fair, close um, solution or clustering of the query that we are trying to complete. Obviously, it's important to take into account other uh, features. For example, Postgre has an extension for vector database, and it's cheaper than Pinecone, for example, and the documentation is bigger. We have a larger community, so you want to pick one of those. But again, it's a trade-off. What are you trying to achieve? Is it velocity, or is it accuracy? The volume of your data is very important. So we need to be very careful on the on what are our goals and what is our motivation to use vector databases. Again, these are more suited for similarity between semantics in our data source. And yep, so that was what I have for today. And yeah, I don't know if you have any question that you would like to
Yes,
know.
yes, I
Yes.
have a question. Uh, if I want to personalize, or I want to include, or I want to add using this vector to interact to elements. For example, I have a chatbot, for example, that consume public elements, and I want to add new rules. I understand, please correct me, that I need to include a vector database that interact with these elements. Am I right?
Yes, even I don't remember which is the name. One of these, Wavite, as mentioned I mentioned to you that their niche is LLMs application, or AI applications in general. They have like a model strictly for different implementations. One of those is chatbot, and they even have like their own implementation or connection to racks, which is like a architecture for LLMs. So yeah, you have multiple options depending on the one you pick, but the majority of them let you do a native connection between the vector database and the LLM you're trying to use. So depending on the, obviously on the use case, because the one that you are telling me is very general, but yeah, most of them have straight connections that you can use and functions that will enhance your LLM model or response.
Okay, my question is related on that. If I have own rules, for example, for one company that need to include new rules or prioritize the answer with that rules, how I need to do in this vector in order that the when make the question to the chatbot, they will go to the LLMs and go to the vector database. How they decide what is the how to prioritize the answer in order that take into account the personalization that I'm going to include. What do I need to do?
Okay, so the one that comes to my mind is there's a function, for example, in Mailbus that is called re-rank. So basically, you take the answer from your LLM and you pick the ones from the vector database, and this re-rank will sort them based on weights, as I mentioned before. So you give a weight to the response from the LLM, and you give a weight to the response from the vector databases, and you build the new vector resulting, or I mean the least resulting for your answer, or if it's only one answer, uh, well, that. So I even can show you that code probably. Give me a second.
Thank you. I believe that you already answered to me. Thank you. Thank you. It's enough to
Okay.
me.
Maybe someone has another question.
Is the re-rank thing? Any other questions?
Looks like no.
So you see, the one who asked me the questions, we have this weighted ranker. So you give each one a weight, and you just pass the hybrid search. Obviously here I pick limit 10, so that's where you see 10 results in the demo. But if you need only one, then you pick one and you give the weight that you want to each of the generation, I mean the LLM or the vector database. Uh, any other questions? Something else you'd like to know?
Oh, hello. I have one question. For example, can I use like a foundational model, like general purpose for embedding, without dedicated model? If it would be slow, or in theory it's possible?
So it's possible for sure. I didn't get the part when you asked. You say something about slow. Sorry, I didn't hear that.
Yeah, like if I use a general purpose model without these dedicated embeddings models, like ChatGPT model. I mean, not the specific model that
Yes, I mean
use
obviously
case.
you
Yeah.
can use ChatGPT even in Milbus, which is the one that I use, has an example with ChatGPT. Obviously, when you say slow, again, is depending because if I don't know how slow could be or how or the price to convert a billion uh, documents into vectors. It is feasible, obviously, but you'll need to take into account things are the nearest neighborhood algorithm you use to create the indexes. So obviously, if you use flat and you're trying to calculate distance in a billion vectors, it will be very, very slow. But if you pick other options as hierarchical, small navigation world, probably it will be doable. It will be costly. Memory, I mean, costly in resources, but yeah, it is possible, and there are examples out there of them.
Okay, thanks.
Another question, guys. Looks like no. Okay, so looks like that's it for today.